This is your presenter Asloob Mudassar, and I am presenting slide number 142 of the course on the laser physics. This is actually part D of the slide. I have presented three parts earlier, that is 142A, 142B, 142C. So I would suggest that in order to comprehend this part, that is 140D, you need to go through parts 142A, 142B and 142C so that you can easily comprehend this presentation. And in this presentation, I am going to present Nd-YAG glass, Nd-YLF, Nd-YVO4 and Ytterbium-YAG lasers. These lasers will be presented in brief. Nd glass laser. Nd glass in Nd glass, glass is the host material which has a lower melting point than that of the YAG and thus can easily be fabricated as an active medium of a larger diameter and length. The concentration of Nd3 plus ion, triply ionized neodymium ion in the Nd glass is roughly double the concentration of Nd3 plus in the Nd-YAG. So the concentration of the Nd triply ionized ion in Nd glass is double that of the Nd-YAG. The pump efficiency of the Nd glass with the flash lamps is roughly twice that of the Nd glass and the YAG of the same dimensions. So you see that here in terms of efficiency, the Nd glass is preferred because it has an efficiency with the flash lamps is roughly twice that of the Nd-YAG lasers. And this is what I am talking about, the pump efficiency for the Nd glass. In Nd glass, Nd3 plus is involved in the laser transitions, whereas 3,4F electrons are again screened by 8 outer electrons, that is 2 electrons from the 5s and 6 electrons from the 5p. These 8 electrons will be involved in the screening of nuclear charge. This is what I have also explained this screening in one of the previous slides. The energy level structure of the Nd glass is quite similar to that of the Nd-YAG, with the mean wavelength lasing at lambda approximately equal to 1.054 micron for phosphate glass. The glass medium usually contains impurities, which results in local field inhomogeneities, which acts as a source of inhomogeneous broadening. Due to this inhomogeneous broadening, the laser transitional line width are broadened by a factor of 40 compared to the Nd-YAG at the main laser wavelength transition of lambda is equal to 1.054 micron. So you see that here I have talked about the inhomogeneous broadening, and the laser transition line widths are broadened by this inhomogeneous broadening by a factor of 40 compared to Nd-YAG. The stimulated emission cross-section at peak wavelength is however smaller than the Nd-YAG by about an order of magnitude. So here I am talking about the stimulated emission cross-section, which is an order of a magnitude smaller than that of the Nd-YAG. A broader bandwidth is a desirable feature in obtaining narrower mode-locked pulses, whereas a smaller cross-section is desirable in obtaining high-energy pulsed system. So you see that in this case, since we have the cross-section, which is smaller in compare with the Nd-YAG, so it means that in the Nd glass, we have the possibility of obtaining high-energy pulsed systems or the pulsed laser system. That is, we can obtain high energy pulses with Nd glass in comparison with the Nd-YAG. The smaller cross-section raises the threshold inversion of the amplified spontaneous emission system of the Nd glass compared to the Nd glass compared to Nd-YVO and more energy per unit volume can be stored in the active medium. So let me read again. The smaller cross section raises the threshold inversion for the amplified spontaneous emission system of the Nd glass compared to Nd-YVO. Here you should have Nd-YVO over here. Nd-YVO compared to Nd-YVO, and more energy per unit volume can be stored in the active medium of the Nd glass system. Glasses have lower thermal conductivity in comparison with YAG by an order of magnitude, which restricts the CW mode operation and pulse repetition rate to lower than 10 Hz. Application area includes laser rangefinders, where low repetition rate is a good choice. Optical amplifiers based on Nd glass have been fabricated for high energy laser driven fusion experiments. So this was all about Nd glass lasers, where we have compared the properties of the Nd glass laser with the Nd-YVO lasers. Now Nd-YLF and Nd-YVO4 lasers. So Nd-YLF is actually neodymium doped yttrium lithium fluoride laser, and Nd-YVO4 is actually neodymium yttrium orthovanadate lasers. There are two important crystalline materials: yttrium lithium fluoride, abbreviated as YLF, and YVO4, which is yttrium orthovanadate, which act as a host material for Nd3 plus ion. Due to poor mechanical and thermomechanical properties of the YLF rods are difficult to manufacture as they easily break. YLF, however, has good thermo-optical properties, including pump-induced thermal lensing and thermal birefringence. The main emission wavelength of the Nd-YLF is 1053 nanometer. The peak gain of lambda 1053 nanometer and laser line width of Nd-YLF match with those of the Nd glass when the glass is phosphate. And for the same reason, Nd-YLF lasers can be mode locked and acts as a first stage pumping for high energy lasers driven fusion experiments. The mode locked operation with the Nd-YLF can be obtained using both lamp and diode pumping. The product sigma tau, with the sigma value equal to 7.6 into 10 to the power minus 19 centimeters, and tau having a value of 98 microsecond, for the neodymium YvO4 is the same as that of the Nd-YVO, and thus the same threshold for inversion. That is, Nd-YVO4 has the same threshold inversion value as that of the Nd-YVO. The gain coefficient of Nd-YVO4 is larger than the Nd-YVO by about a factor of 4. The Nd-YVO4 has reduced sensitivity to cavity losses. Nd-YVO4 can be pumped longitudinally and transversely. Longitudinally diode pumped Nd-YVO4 in CW mode gives optical power exceeding 15 watt and which are commercially available. Nd-YVO4 takes precedence over the Nd-YVO in common areas of applications. Now I am going to present Ytterbium-YAG laser. Yb-YAG lasers or ytterbium doped yttrium aluminum garnet laser. The electronic configuration of ytterbium with reference to the electronic configuration of xenon is the electronic configuration of xenon, along with we have 4f14, 6d0 and 6s2. This is the electronic configuration of the ytterbium. In the ionic bonding of ytterbium with the synthetic garnet, that is with the synthetic YAG, 1 4f electron and 2 6x and 2 6s electrons are involved. So you see that from here you can notice that 2 6s electrons and 1 electron from the 4f, these 3 electrons will be involved in the ionic bonding. And so the electrons that are left in the 4f orbital will be 4f13 will be left. Or you can say that a single hole is created in the 4f orbital, because the rest of the orbital is complete except that there is a one vacancy, and we can treat that vacancy as a single hole. In the ionic bonding of the ytterbium with the synthetic garnet, 1 4f electron and 2 6s electrons are involved, and ytterbium presents itself as a triply ionized ion, that is Yb3 plus, with 1 electron short of a full 4f shell. That is, the 4f shell is missed by 1 electron, so we can say that there is a one vacancy or in the 4f shell. The missing electron in the 4f shell may be considered as a single hole. The simplified energy level diagram of the ytterbium YAG is shown in figure number 3. And you know that this single hole which is created in the 4f shell may be considered as a single electron as far as the spectroscopic notations are concerned. And in that single electron, what we have is that corresponding to so it means that we have a single electron in a 4f shell. And you know that f, when we have f, it means that we have the value of capital L is equal to 3. So capital L, which is the orbital angular momentum quantum number, will be 3 for this case. And since this is we are treating this single hole as a single electron, so it means that for the single electron, the total spin angle, the total spin quantum number capital S will be equal to half. So we have now two values: capital L is equal to 3 and capital S is equal to half. And you see that when these two will combine together, that is, we have capital J is equal to mod of capital L plus minus capital S. So when you add the two quantities, that is 3 plus half, you get 7 half over here, which is written over here as a subscript. And if you subtract 3 minus half, then you will get the quantum number, total quantum number equal to 5 half. So we have two terms obtained. This capital F indicates that it corresponds to the spectroscopic terms corresponding to capital L is equal to 3 is capital F. So we have capital F over here, and then we have two terms, capital F with the 7 half and capital F with the 5 half. So when capital L, which is 3, will add with capital S is equal to half, then you have 7 half, and when you subtract capital S is equal to 1 half from capital L is equal to 3, you get 5 half. And this 2 is the multiplicity, because we have a single electron with the capital S is equal to half, so the multiplicity is 2, that is doublet. Because you for the multiplicity, the formula is 2 times capital S plus 1. So capital S is equal to half, so you have 1 plus 1 is equal to 2. So this is the multiplicity which I have written as a superscript. So the two terms have been shown, that is the two manifold terms, 2f5 half and 2f7 half. And you can see that this is the figure number 3. Simplify, the caption is a simplified energy level diagram of the ytterbium YAG laser. And you can see that I have shown two main manifolds of the levels, 2f7 half and 2f5 half. The pumping is done at the wavelength of 941 nanometer, and 968 nanometer. So the pumping is done from the ground state using pumping wavelengths to be equal to 941 nanometer and 968 nanometer. And the laser system and the laser wavelength is obtained at 1.03 micron or 1030 nanometer. The splitting of the sub levels in F72 and F52 have been shown in wave numbers or in 1 over lambda notations or in centimeter inverse. You can see that I have the lowest level in F7 half is 565 centimeter inverse. The next one is 612 centimeter inverse. The next one is 785 centimeter inverse. And in the F5 half levels, the lowest one has an energy corresponding to 1327 centimeter inverse. The next one has 10,624 centimeter inverse, and the next one has 10,679 centimeter inverse. And the lowest of these for the F5 half is 10,327 centimeter inverse. And the laser operation will be obtained. The lasing wavelength is 1030 nanometer or 1.03 micron. And the pumping lasers are, that is the pumping wavelengths for the pumping source will be 941 nanometer and 968 nanometers. The ground state manifold, which is 2F7 half, and the excited state manifold, which is 2F5 half, are the result of interaction of one hole in the 4F and the crystal field. There are two absorption lines, but the line 941 nanometer is broader than the 968 nanometer line, and thus preferred for pumping by an intense source using diode as a pumping source. So you see that the two pumping wavelengths will be 941 nanometer and 968 nanometers from the ground state to the upper levels of F5 half. The intense emission occurs at 1030 nanometer. So it should be corrected as here 1.03 micrometer or 1030 nanometer. So please make a correction over here. It should be 1030 nanometer. Or 1.03 micrometer that I have indicated over here in the figure. So if you read in micron, it will be 1.03 micrometer. And if you read this in terms of nanometer, it will be 1030 nanometer. So this is a typing error, I think. So it should be 1030 nanometer or 1.03 micrometer. The lower laser level for the line 1.03 micrometer remains strongly coupled with the other lower levels and is in thermal equilibrium. The system at 1.03 micrometer thus acts as a quasi three-level laser system. The lifetime of the upper laser level is tau is equal to 1.16 millisecond, which is long enough for the Q switching and pulsed laser operation. More doping level of ytterbium in Yb-YAG is possible than the doping of the Nd in Nd-YVO4, and at the same time avoiding fluorescence switching due to ion-ion interaction. At the lasing wavelength of 1.03 micrometer, you see that here I have corrected the mistake, which is 1.03 micron. The line bandwidth is quite broad, of the order of 86 centimeter inverse, which is quite appropriate for mode locked operation in picosecond. So you see that the bandwidth, larger bandwidth is required when we talk about the mode locked operation. The pulse operation is based on amplified spontaneous emission. which allows a lot of energy to be stored due to low stimulated emission cross section. So this point is very important, that since you have a low value of the stimulated emission cross section for ytterbium-YAG laser, so it means that you can store more energy in the upper states. So ytterbium-YAG is pumped longitudinally using indium gallium arsenide or gallium arsenide strained quantum well lasers at a pumping wavelength of lambda p equal to 943 nanometer. So this 943 nanometer is what I have shown over here. For example, corresponding to that one. So the pumping is done at 943 nanometer over here. Ytterbium-YAG is also pumped by a Ti-sapphire laser. Average pump power above 60 watt has been obtained. The system has very good optical efficiency, which is due to very high pump quantum efficiency. And the pump quantum efficiency is given by eta q is equal to h nu over h nu p, where nu is the frequency corresponding to the transition, and nu p is the frequency corresponding to the pump frequency. So h nu over h nu p is equal to lambda p over lambda is roughly equal to 92%. So very high quantum efficiency. Due to its quasi three-level nature and low stimulated emission cross-section, which is a negative point for this laser, ytterbium-YAG covers almost all the applications areas of the Nd-YAG. So all the applications where Nd-YAG is a laser is required, we can use ytterbium-YAG lasers there also, and is preferred where pumping source is a diode operating at about 1 micrometer is available. So if the pumping source is the diode laser, we can prefer ytterbium-YAG laser over the Nd-YAG laser in all the applications where Nd-YAG is preferred or where Nd-YAG is used. And there we can prefer the ytterbium-YAG laser provided the pumping source is a diode laser. In the next slide, I shall be presenting ytterbium-YAG, ytterbium, erbium, glass laser, erbium-YAG laser, tholium, holmium, YAG laser. So these lasers will be presented in the next slide. So this is the end of slide number part D of the slide number 142.